Good morning, class. Today is Monday, May 11th, and let's get started with some science. So we are on our ocean surface currents lab, and when I do this lab in the classroom, I actually have students follow the directions that are in their Ultimate Science notebook as kind of a understanding of how to read scientific directions and some more independence. Today, obviously, we can't do that, so that's just why there's so many directions on your lab page, and it takes up 3 pages as opposed to 2. So the first question we have is, which of the following causes surface currents? Is it A, heat, B, convection, C, wind, or D, animal life? So I want you to think in your head, which one of those is it? Circle it on your paper. I'm going to give the answer in 3, 2, 1. It's actually C, wind. Number 2. And again, my expectation is that you're doing this in your Ultimate Science notebook, or you are doing this on a spare sheet of paper. Number 2, which of the following causes deep ocean currents? Is it A, density, B, wind, C, animal life, or D, stored energy? Think about that answer in your head. Circle it on your paper. Giving the answer in 3, 2, 1. It is actually A, density, because remember, what causes those deep ocean currents is that cooling water sinking and that hot water rising, that higher salinity water sinking, that less salinity water rising. So it's a convection current. It's like that conveyor belt that we see at the grocery store. Number 3, which kind of energy would this be an example of? And you might not have learned this yet, and that's okay. Is it A, chemical, B, potential, C, mechanical, or D, radiant? So think about what that would be in your head. I'm going to give an answer in 3, 2, 1. It is C, mechanical. So our answers here were C, A, C, CAC, if you will. So now we're going to talk about differences in surface currents. So I'm going to take my giant cooking tray that I have in front of me. I'm just going to show these off. So again, with all lab experiments that we're doing during the quarantine, you do not have to do them at home. You do not have to do them at home. You do not have to do them at home. I'm going to say that every single video just to make sure that we understand. If you want to do them at home, I'm also going to walk you through them. So those are your 2 options. You may do this at home with the materials that I'm describing, or 2, which is totally fine, you can watch my video and do the lab visually with me. So we have a giant turkey tray. In my case, I don't have any turkey trays and I didn't want to go to the grocery store for a special trip. So I'm using just a regular cooking tray that has a Pyrex pan that has some kind of edge. You should be able to see through it, or at least see over it. You need to fill it with about 2 centimeters of water. You don't have to measure. You don't need a ruler. You just need some water in the bottom of your tray. Then we're going to take our straws and blow at different speeds and record our observations. I have my reusable straw because it's good for the environment, but you can use a plastic straw as well. So the question that we're asking ourselves is, which speed of blowing will create the biggest waves or simulated surface currents? Safety. No 2 students should be blowing with the same straw. This is especially true during the coronavirus, even with your own family. Each student should have their own straw. And also, please be sure you do not blow on a straw that has been on the floor. So if this drops on the floor, touches your dog, whatever, make sure you throw it out or wash it if it's a reusable straw. So what is your prediction? Well, blowing hard, blowing softly, blowing hard with a rock in the way, blowing softly with a rock in the way, which of those will cause the biggest simulated surface currents? What is our independent variable? What is our dependent variable? What do we need to keep the same to keep the experiment fair, or what's a constant? And what type of data are we collecting? Pause this video. I want you to fill out all of those things and come back to this video when you're ready for the answers. So if you're on this video right now, my assumption is you filled in this section of your lab sheet. Let's go through it together. Our independent variable, what we're changing is the speed at which we're blowing / if there's a rock in the way, so the conditions that we're blowing. The dependent variable, how are we measuring it? We're looking for those surface currents. We're looking for those waves on the top of our water. What do we need to keep the experiment fair? So each time we're doing this, notice that my tray is not changing. It's staying the same. I'm really glad that this angle is kind of working so we can see. I want to start with the same baseline, right? So I want to make sure my water calms down before I start any of this. My straw is staying the same. I am the same person blowing for all of these times. Those are all things that we need to keep the experiment fair. So the type of data that we're collecting here is qualitative data, and that is because our data has words and we're not measuring numbers. Now, if we could actually pause and record, how high the waves are going, or, what kind of force there was behind that, that would be a totally different experiment. We would have quantitative data with numbers, but this one we have qualitative with words. So let's move along. These are the answer key, by the way. Pause if you need to get any of those answers again. Let's start with blowing hard. So I have my tray, I have my thing. When we're doing this, we want to blow from one corner to the other. So this is blowing hard. Ready? 3, 2, 1. So it's actually getting all over my computer, and some is leaving, and that is one of my qualitative observations. I'm going to wipe that down real quick before we have any permanent damage. Science is messy, as I like to say. So I'm seeing a big divot when I'm blowing hard, and I'm seeing the rest of it kind of blowing up. I don't quite see the ripples. I see more waves. Now let's see what happens when I blow softly. Make sure that you're recording your observations on that table. I'm just going to show you what that looks like again so that we're clear. So right to the right here, you should see that observations. What do you see? We're recording qualitative observations. So now I'm going to try blowing softly. 3, 2, 1. So what's cool about the blowing softly is you can see, or you can even draw as part of your observations, that we see much more ripples, right? The water is more interacting with each other, and it's interacting more with the edges of the container. It's not able to overcome that difference. Okay, so now I went outside my house and I got a rock, and I'm going to put a rock inside of my container. Quick safety tip: if you are using a big rock like mine and in a glass container, you want to make sure you're careful, because this glass container can break if you just plop it in. Always be careful. You don't want to have water and technology together. So the first thing we're going to do is we are going to do, and I'm going to back it up this time just to make sure that this is not as crazy. I'm blowing again in the same direction to keep my constant the same, and we have a rock and we're blowing hard now. Let me show you where this should go in your Ultimate Science Notebook. We're still recording those visual observations. 3, 2, 1. So if you can see, the waves are still going over my rock, but they're also going around my rock. And I still managed to get some on my computer. Go me. So there's this overcoming the rock, and there's also this around the rock. Now let's try going softly with the rock. I'm going to bring it closer so that you can actually see a little bit better, because this one doesn't tend to. And this is a big point. This right here, make sure you're paying attention, because this is kind of the whole point of the experiment. So if you look really carefully, this part of my water isn't being disturbed at all. It's staying completely calm. The water is going around my continent, which is very similar to what we talked about yesterday with surface currents and deep ocean currents. When there's a continent in the way, our water has to bend around. So the key kind of takeaway of this lab is that surface currents are affected by the speed of the wind, and they're also affected by what land masses are in the way. In this experiment, we're representing that with a rock. So you see it's hitting here, and that energy is not lost. It's going on either side of the rock. All right, so continuing on, make sure you write your conclusion. Was your hypothesis verified or falsified? So when you predicted which one had the biggest waves, which one was the truth? And honestly, for me, I think it was the one with blowing hard and the rock in the way, because not only do we have the force or the energy from the straw and the air that we're pushing out of our lungs, but we also have that friction or that hitting of the rock when it's in the water. Moving on, so now turn the page. We're going to do some deep ocean currents. And it says, use the words dense, deeper, closer, and convection to describe what is powering the deep ocean currents in the picture below. What I want you to do is, and I really like that it's in color here, because it's really difficult to see and do this without the color. But notice how the blue lines are on the bottom, and then it's slowly heating and rising back up to the top. So pause this video, answer those questions, and come back when you're ready. So I'm assuming that you're ready for the answers if you're here with me now. As water hits the rock, it moves as waves hit the rock, it moves it deeper in the ocean. And we see that with those arrows pointing downward. It gets colder, which makes the water more dense. As it becomes hotter, it becomes less dense and comes closer to the surface. So we didn't use any convection. It was kind of a tricky word in there. Those are the answers for that particular section. So now it says, take a turkey baster and a beaker of warm water with red food coloring and a beaker of cold water with blue food coloring. Take your ocean in your turkey tray and add another 4 centimeters of water. Stick your turkey baster in the warm water, suck it in place into the ocean starting from the bottom. Observe what happens in the space below. So I have here my cold water. I'm just going to give you a measurement. It's in Fahrenheit because this is my food thermometer. So obviously I measure my food in Fahrenheit because we're in the United States. I know that's not very scientific. If you're doing this at home, you don't need to measure the temperature of your water. I just want to show you that these are hot and cold because if we were in a classroom, I'd have someone come up and actually touch it. So my cold water, which I got it to be cold by putting an ice cube in it, is 44 degrees Fahrenheit. And my warm water, which I put in the microwave, is 124 degrees Fahrenheit. And my ocean water is right in between those two, it's 71. So that should give us pretty good contrast of these different water temperatures, which should give us the result that we're looking for with this experiment. So, and if you look at this water in here, you'll notice that they're having us put it towards the bottom. Now, in an ideal planet, we would have red and blue food coloring, but this is quarantine, people, so we're doing the best that we can. I'm going to use up some leftover pink food coloring for my hot water. Notice that water is a compound, just some review from Matter and Change, right? Because it's H2O, it's one kind, it's more than 2 elements bonded together. Once I add the pink food coloring, though, it becomes a solution. I'm going to use my turkey baster to mix it around. And remember, it's a solution because these two are not chemically combined. And I could separate them if I had enough time and evaporation supplies. But it's a solution because they're not chemically combined and they're completely dissolved together. Ooh, a piece of my turkey baster came off. That's not great. Okay, so I'm going to stick this in. I'm filling up my turkey baster. Hopefully we can see this. It would be easier to see if you were at home, but I want you to just kind of notice when I put it. Oh gosh, this is like the worst turkey baster ever. I need to replace this when I move. Okay, ready? So notice what happens when I put it towards the bottom. 3, 2, 1. So I put it in at the bottom. And if you notice, it's coming directly to the top. And let me see if I can even pull this up and get like a side angle. So you see all that red food coloring is raising to the top of my water. Why is this? My turkey baster almost fell over. Let's review our song. Liquid to a solid, it is called freezing. Solid to a liquid, it melts back again. Liquid to a gas is called evaporation. Gas to a liquid is condensation. If you do this lab, you're going to have like purple, bluish hands for the rest of the week, which is fine. Science is messy. And so why this is happening is because my molecules are further apart. Remember, they're closer to being a gas than they are being a solid. And so because of that, they're less dense, they're further apart, and they're raising up to the top. Let's do the same thing with our blue. Again, I don't have blue food coloring, so we're going to use green. Looks awesome. And let's show this in 3, 2, 1. Putting the green on top. And you notice it doesn't even stay on the top at all. It completely sinks to the bottom, even if I pour it. Look, it's almost completely underneath that red. It's going straight to the bottom. So make sure you fill in all the pieces of this lab sheet. And thank you so much for tuning in. This is the one we just did. Here's the answer key in case you need it. And thank you so much for tuning in. Have a great rest of your day.